picture this scenario. It's a Tuesday afternoon. You're a developer. You've been staring at a monitor for 6 hours straight.
Mm-hmm. The coffee is worn off.
The coffee is gone, your back hurts, and you have this deadline just looming at 5:00 p.m. You're building a Python application, maybe a content management system, maybe a documentation tool, and you realize you need a spell checking feature.
A totally standard requirement.
Exactly. And you are not going to write a spell checking algorithm from scratch. That would be insane.
No one reinvents the wheel. It's the whole point of open source.
Right. So you do what you've done 1,000 times. You open your terminal, the cursor blinks, you type pip install, and you type a name that sounds right. Maybe Spellchecker P. It sounds official. It sounds like the thing everyone probably uses.
It have pi at the end. It must be the one.
It must be. You hit enter, text scrolls by, successfully installed. You import it. It works. You meet your deadline. You go home.
It's a moment of pure muscle memory. We don't even think about it. It's the digital equivalent of walking into a grocery store and just grabbing a gallon of milk off the shelf.
Yeah.
You trust the store. You trust the brand on the carton. You don't take a sample of the milk to a lab to test for arsenic before you pour it on your cereal.
Of course not.
You just trust that the whole supply chain works.
Exactly. But in this specific case, and we're talking about late January 2026, that simple, mundane act of grabbing a package off the shelf was, well, it was a trap. For over 1,000 developers, that milk wasn't milk.
It was poison.
It was poison. And it wasn't just poison, it was a wiretap. It was a set of keys to the front door of their company.
And that's a terrifying thought because it exploits the one thing the entire open source ecosystem is built on.
Trust.
Trust. We just assume that if it's on the Python package index or PyPI, and it has a normal sounding name, it's probably fine.
And today, we're diving deep into that broken trust. It's a fascinating and, frankly, a very scary story of deception in the software supply chain. We're looking at a specific case study involving two malicious packages, Spellchecker B and Spellchecker. We're going to unpack how a threat actor hid a Remote Access Trojan, a RAT, inside a dictionary file. And trust me, the specific hiding spot is wild. We're going to talk about how they played the long game with these dormant versions to groom security scanners.
Which is a whole other level of patience.
It is. So. And then we're going to pivot to something that sounds like it was ripped out of a cyberpunk novel, but is happening right now. AI agents hallucinating fake packages and hackers squatting on those hallucinations.
It's called slop squatting, and it fundamentally changes the defensive landscape. But we'll get there.
We will. We have a great stack of sources for this deep dive. We're pulling primarily from a really detailed investigation by Ravi Lakshmanan from the Hacker News, published in late January 2026. And that report draws heavily on the technical analysis from Charlie Erickson at the security firm Aikido, as well as some earlier findings from a group called Helix Guard. So we have the technical breakdown, we have the timeline, and we have the broader context all right here.
And I think the mission for this deep dive is really to update our mental models. If you're still operating on the security model of, check the star count on GitHub or glance at the name, you are about 3 years behind the threat actors.
That's a scary thought.
It is. We need to understand the sophistication of these attacks to have any real hope of stopping them.
Okay, so let's start with the trap itself, the bait. We have these two packages, Spellchecker P and Spellcheck Pay.
Very, very subtle naming. One has the error, one doesn't. They're covering both likely typos.
Right. And to the untrained eye, or heck, even the trained eye that's just moving too fast on a Tuesday afternoon, these look totally normal. In fact, they look helpful.
Well, that's the whole point. They are masquerading as legitimate tools. They're trying to mimic the structure and the naming convention of a real, safe, and very popular package called PySpellchecker.
Ah, okay. So there is a real one?
There is a real one. And if you're typing fast, or if you just misremember the name, Spellchecker sounds perfectly plausible. It sounds descriptive. It sounds like it should exist.
It's classic typo squatting, but it seems like they went deeper than just the name. When you look at the package structure, they actually tried to make it look like a real project. It wasn't just, a blank shell with a virus in it.
Exactly. And this brings us to what we can call the anatomy of the deception. Usually, for years, when we talk about malware and Python packages, we talk about one file in particular.
The init.py file.
The init.py file.
Right. And for listeners who might not be Python developers, init.py is the file that basically tells Python, hey, this directory is a package. It's the startup script. It runs automatically the second you import the package into your code.
Correct. It's the handshake. And historically, that is the front door for malware. Lazy attackers, or let's say less sophisticated attackers, would just dump their malicious code right there in init.py.
Just a line in there that says, download this virus and run it.
Pretty much. And which I imagine is pretty easy to catch.
You'd think so.
It's incredibly easy to catch. Every security scanner, every antivirus, every static analysis tool on the planet knows to stare at init.py like a hawk.
Okay.
If you put a URL to a suspicious server or a big blob of obfuscated code right there in the startup script, the red lights start flashing immediately. It's the first place they look.
So this attacker knew that. They knew the front door was being watched.
They did. So they decided to come in through the library window, so to speak. They went looking for a place in the package structure where no one looks, a place that's boring.
A place that's supposed to be boring.
A place that's meant to be full of, well, gibberish data anyway.
They hid it in the dictionary.
Specifically, a file located at resourcecu.json.gz.
Okay, let's unpack that file name because every single part of it feels calculated.
Yeah.
Resources, that implies it's just data, not executable code.
Right. It's not a .py file. It's a resource.
.gz means it's compressed, like a zip file, so you can't just read it as plain text.
Another layer of obfuscation.
And U, that stands for Basque, right? The Basque language.
Exactly. UU is the ISO code for Basque. Now, think about this from a camouflage perspective. The legitimate Spellchecker project, the real one, actually does contain dictionary files for various languages.
So it should be there.
It belongs there. Having a file named uu.json.gz isn't suspicious in itself. It fits the expected pattern of a spell-checking library.
It's like having a tires folder in a project about cars. It makes sense.
It makes perfect sense, and it provides a few layers of cover. First, as you said, it's compressed.
Yeah.
To see what's inside, a security scanner has to take the extra step to unzip it first. That adds friction. Many lightweight scanners, or ones in a hurry, might just skip compressed files to save time and resources.
Sure, they're looking for the low-hanging fruit.
Exactly. Second, it's a resource file. Scanners expect JSON files to contain data key value pairs, strings, numbers, not executable code.
Right.
Their parsers are looking for code structures, not data structures.
Right.
And third, well, how many developers in the United States or Germany or India are actively auditing the Basque language frequency list?
I'm going to go out on a limb and say 0. I mean, the Basque language is fascinating, but statistically, it is a very small demographic compared to English or Spanish or Mandarin users.
Precisely. If you corrupt the English dictionary, users might notice immediately, hey, why is the spell checker flagging the word "the" or something like that?
Yeah, that would be a pretty obvious bug.
But if you corrupt the Basque dictionary, it just sits there on the hard drive, completely unnoticed. It's a sleeper agent in the most literal sense.
It's like hiding a gun inside a hollowed-out book on a library shelf.
Yeah.
But not just any book, a book on, like, 18th century basket weaving techniques that nobody has ever checked out.
That is a perfect analogy.
Yeah.
The book looks like a book. It feels like a book.
Yeah.
But inside, it's a weapon.
Okay, but here's the thing. A gun inside a book doesn't fire itself. You have to open the book, take the gun out, and pull the trigger.
Right.
And that is the second part of the cleverness here. The code in the rest of the package needed a way to extract that payload from the dictionary and run it without being obvious about it.
Exactly. Because if the main code just had a function called execute hidden virus from the dictionary, well, that's not going to pass a scan.
No. Even a simple text search would find that. If the code said, open json.gz and run the hidden virus, the scanners would catch that command. Open file plus execute equals malware. So how did they trigger it?
They used a function called test file.
Test file, that sounds incredibly mundane.
Doesn't it? It sounds like a diagnostic tool. It
Yeah.
sounds like something a developer left in for debugging. Oh, I'm just testing to make sure the dictionary loads correctly. It looks completely harmless.
You'd see that in a code review and you wouldn't even blink.
You'd probably think, they should clean that up before production, but you wouldn't think malware.
So what did test file actually do?
Well, normally, maybe nothing. But the malicious behavior was only triggered when this function was called, with a very specific set of parameters. The research from Aikido highlights the exact combination.
Like a secret code.
It was a combination lock. The command had to be test file, EU, UTF, AST, spellchecker.
Okay, let's break that down.
Yeah.
U obviously tells it to open the Basque file.
Correct. Target acquired.
UTF tells it the character encoding, which is standard.
Standards.
And spellchecker, that's the key.
That is the specific key inside the JSON file where the malware was hidden. So imagine this JSON file. It looked like a normal list of words and their frequencies. You'd see apple, 50, hello, 100, whatever.
Right.
But buried deep in that list was a special key, Spellchecker. And the value associated with it wasn't a number. It was a massive, massive string of base 64 encoded text.
And base 64 just looks like a random jumble of letters and numbers to a human, or even to a simple scanner, right?
Exactly. It just looks like data. It's not structured like code.
Yeah.
But if you pass it through a decoder, it turns back into executable Python code.
Wow.
So the test file function acted as that combination lock. If you ran it with random arguments, nothing happened. It would probably just fail gracefully. But if you gave it that secret handshake, CO, OTF8, Spellchecker, it unlocked the payload.
It goes into the file, finds that specific key,
Decodes the base 64 string.
and boom, it executes it.
In memory, which is another way to avoid detection. It's not writing a suspicious .exe file to your disk. It's just running code that's now living in your computer's RAM.
That is incredibly specific. And it really shows a level of obfuscation that's designed to bypass static analysis tools. A tool scanning the code might see test file and just ignore it because it looks like a utility function. It doesn't look like download virus now.
Exactly. It's designed to look boring. And it gets even more interesting and maybe more sinister when you look at the timeline, because the attacker didn't just upload this fully weaponized version on day one.
No, they played a waiting game. This is the part of the report that really creeped me out, the sleeper phase.
Right. According to the analysis by Charlie Erickson at Aikido, the first 3 versions of this package were effectively dormant.
Okay, define dormant for us in this context, because that sounds like something out of a spy movie.
It really does. The payload was there. That Basque dictionary file with the hidden base 64 code, it was present in those early versions from the very beginning.
So the bomb was in the building.
The bomb was in the building. But the trigger mechanism, the part of the code inside test file that actually executes it, was missing. The code in those early versions would fetch the payload, maybe even decode it into memory, but then it would just do nothing with it. It wouldn't run it.
Wait, why go through all the trouble of hiding it if you aren't going to use it? What's the point?
Credibility, reputation building. It's all about gaining the automated systems.
How so?
Imagine an automated security scanner that runs on PyPI. It downloads version 1.0 of Spellcheck Pi. It unzips everything, scans all the .py files, and it sees code that opens a resource file and decodes some data, but never executes it.
So it doesn't see anything explicitly malicious.
It sees nothing malicious. It's not making a network call. It's not executing a shell command. It marks the package as clean. Then version 1.1 comes out a week later, still clean. Version 1.1.5, clean.
The repository is building a history of safe releases.
It's grooming the security systems. It's establishing a pattern of legitimacy. And maybe some early adopter developers install it, use it, and report no problems.
Totally.
Starts to look like a normal, if quiet, open source project.
And then the switch gets flipped.
And then the switch gets flipped. January 21, 2026.
That's the date.
Version 1.2.0 of Spellcheck PyPI is released. And in this specific version, the attacker adds the final piece, the obfuscated execution trigger. Now, the moment a user imports Spellchecker, which is the very first thing you do after installing the package, that test file mechanism fires automatically. The lock gets the right combination.
So for those first few weeks, anyone who downloaded it was technically safe, even though they were carrying this time bomb?
Correct.
But anyone who ran pip install upgrade, anyone who updated to 1.2.0, or anyone who installed it fresh after January 21st?
The bomb went off.
And the numbers. I think the report said we're looking at a little over 1,000 downloads collectively before it was caught and removed.
Right. Now, in the world of consumer apps, where we talk about millions or billions of users, 1,000 sounds small. It's easy to dismiss. You might think, oh, only 1,000 people.
But that's the wrong way to look at it.
It's completely the wrong way to look at it. You have
Yeah.
to remember who these people are. These are not random internet users. These are developers. These are software engineers.
Right. And where do developers work? They work inside companies, they work on production servers, they have access to databases, to cloud credentials, to internal networks, to customer data.
Exactly. One compromised developer laptop can be the entry point to an entire enterprise network. That one pip install could happen on a machine that has the keys to the entire kingdom.
So in the supply chain context, 1,000 downloads doesn't mean 1,000 infected home computers.
No. It could easily mean 1,000 compromised organizations. It could be build servers and CI/CD pipelines. It could be data scientists working on sensitive models. It's not about the quantity of infections. It's about the quality and privilege of the targets.
Okay, so the trap is sprung. You've imported Spellchecker. The test file function runs. It decodes the payload from the Basque dictionary. What happens next? What is this thing actually doing on the system?
Right, so the code that was hidden inside the dictionary wasn't the final boss, so to speak. It was just a downloader. Stage 1.
It's a stepping stone.
It's a stepping stone.
Yeah.
Its only job was to reach out to the internet and fetch the actual Remote Access Trojan, the RAT.
It calls home.
It calls home. The investigation identified the specific domain it was calling out to. Updatenet.work.
Update, again, just so generic, so
Yeah.
boring. It sounds like a legitimate Windows service or something.
It's designed to blend in.
Yeah.
If a security analyst sees that in a network log, they might not think twice about it. And when the researchers looked at the registration data for that domain, they found it was registered in late October 2025.
Wait, the attack went live in January 2026, so they set up the C2 infrastructure almost 4 months in advance.
That suggests premeditation. This wasn't a spur-of-the-moment script kiddie prank. This was a planned operation. They set up the command and control server, they let the domain age a little bit so it wouldn't look brand new to security filters, and then they just waited.
That's patience.
That's professional. And when the researchers looked at where updatenet.work was actually pointing, they found an IP address, 172.86.73.139.
Okay. And does that IP tell us anything?
It does, potentially. This is where the attribution game gets a little murky, but very interesting. That IP address is managed by a hosting provider called Router Hosting LLC, which also operates under the name Cloudsy.
Cloudsy. I feel like I have heard that name in security reports before. It has a reputation.
You likely have. The report from the Hacker News explicitly mentions that Cloudsy has a history of offering services that have been used by, and I'm quoting here, nation-state groups.
Okay, so let's be very careful here. We are not saying Cloudsy is a malicious company, and we're definitely not saying this was a nation-state attack.
Absolutely not. That's a critical distinction.
Yeah.
Hosting providers are like landlords. They rent out space. Sometimes bad guys rent the apartment.
Sure.
But what you find is that experienced threat actors tend to gravitate towards certain providers that perhaps have, let's just say, lax or know your customer policies, or are based in jurisdictions that are slower to respond to abuse takedown requests.
They look for safe havens.
They look for operational security. The fact that this infrastructure was hosted there signals a certain level of sophistication, or at least a knowledge of the preferred vendors for this kind of activity. It's another piece of the puzzle that says this wasn't an amateur.
Okay, so the downloader connects to this server hosted on Cloudsy. It grabs the RAT and it executes it.
Yeah.
What can this thing do? What are the capabilities of this RAT?
It's a Python-based remote access Trojan. So it effectively gives the attacker hands-on interactive access to the developer's machine.
Like they're sitting at the keyboard.
Exactly. The first thing it does is fingerprint the host. It figures out, where am I? Is this a Mac? A Windows machine? Am I inside a corporate network? What's the username that's logged in? All of that basic reconnaissance.
Okay, so it's gathering intel.
It's gathering intel. Then it parses incoming commands. It basically creates a loop where it constantly polls the server asking, what do you want me to do next?
Yeah.
And the server can send back shell commands.
So they can do anything. They can OLS to browse your files. They can cat your SSH keys. They can look at your environment variables for cloud API keys.
Anything you can do on your terminal, they can do remotely and silently. And since this is running in the context of a developer who just ran pip install, it likely has all the permissions of that user.
And if you're one of those people who uses sudo pip install,
Well, then they have root. And it's game over.
that is a nightmare scenario. And the scariest part, as we touched on, is that this wasn't a one-off event. This attacker didn't just try this once, fail, and give up.
No. That's why we look for patterns in these things. The investigation directly linked this to a discovery from back in November 2025 by HelixGuard,
Okay, so a couple months earlier.
a couple months earlier. Back then, there was a package called Spellcheckers with an S, plural.
Ah, so they went from Spellcheckers in November to PyPI and PyPI in January. It's an evolution.
It's the same modus operandi. The report says it had the same ability to retrieve and execute a RAT payload. It's almost certainly the same threat actor or threat group, just refining their technique.
So they get caught. PyPI takes the package down.
They burn the infrastructure, they wait a few weeks, they register a new domain, tweak the hiding spot maybe, upload a new package with a slightly different name, and try again.
It's a relentless game of whack-a-mole. But it's not just happening in the Python ecosystem, is it? I was really struck by how the report mentions that this is part of a much broader trend across other ecosystems too, specifically NPM.
Right, and that's critical context. This isn't a Python problem, it's a supply chain problem. While Python and PyPI are huge for data science, machine learning, and back-end systems, NPM is the heart of the web. Almost every modern website you visit runs on code from NPM.
And the attacks there seem even more targeted.
They do. The report highlights concurrent attacks happening there that are really specific. For example, there was this industrial phishing campaign.
Yeah, I saw this list of package names, Flocchiali, Opresk, Prizan. These names, they just look like gibberish, like a cat walked across the keyboard.
They do, but they weren't trying to type a squat a real package. They were just trying to get these packages into specific build processes. And these packages contained a single JavaScript file. When that code was loaded, it served a fake Microsoft-branded login screen.
A fake login screen inside a code package. How does that work?
Imagine you're an employee at, say, an energy company. You're using an internal web-based tool. That tool has a dependency on one of these malicious packages. Suddenly, a session timeout window pops up that looks exactly like a real one. Microsoft 365. Please sign in again to continue.
And you wouldn't think twice. You'd just type in your username and password.
You type in your password and your MFA token, and you just handed your corporate credentials directly to the attackers.
And the report says they were targeting specific sectors.
Yes. The researchers identified targets in industrial and energy companies located in France, Germany, Spain, the UAE, and the US. This is highly targeted. This is spear phishing delivered via code dependencies, which is a whole new level of scary.
That is wild. And there was another one mentioned, a Stealer campaign.
Yes, a package called ANSI Universal WE. Again, it sounds like a boring, legitimate user interface library for coloring text in the terminal or something.
Totally. Something you'd add to a project without a second thought.
But it was a Trojan. It was deploying a Python-based stealer that the researchers dubbed Gwagon.
G-Wagon. Like the Mercedes-Benz SUV.
Apparently. A flashy name for a really nasty piece of malware. It was a vacuum cleaner for secrets. It targeted everything. Web browser credentials, saved passwords, cookies, crypto wallet.
Oh, of course.
Cloud credentials from AWS or Azure config files, Discord tokens. It exfiltrated all of it to a cloud storage bucket on a platform called AppWrite.
So it seems like the entire open source ecosystem is just under constant siege. You have the Spellchecker, RATs in Python. You have these industrial phishers in NPM. You have the crypto stealers. It's a lot.
It is a lot. But there is one more layer to this story that I think is the most significant for the future of security. And it's the one that moves beyond the human element. We've talked about humans making mistakes, typo squatting, trusting the wrong package because you're in a hurry.
Right.
But what happens when the mistake isn't human?
You're talking about the AI angle.
I am.
The report mentions this term, and I have to say it's a great term. Slop squatting. It sounds disgusting.
It's a visceral term, isn't it? And it comes directly from that Aikido research by Charlie Erickson.
So let's break this down. What on earth is slop squatting?
To understand slop squatting, you have to first understand the concept of hallucination in large language models, or LLMs. We all know that AI sometimes just makes things up.
Right. You ask it for a legal precedent, and it invents a court case that never happened.
Exactly. It sounds very confident, but it's presenting total fiction as fact. Well, it turns out AI does the exact same thing with code libraries.
How so?
If you go to a chatbot and you ask it, hey, write me a Python script to process this very specific niche data format, the AI might say, sure, that's easy. Just pip install Data Processor Plus and then run this code.
But Data Processor Plus doesn't exist. The AI just invented the name because it sounds like a real package that should exist.
Precisely. It hallucinated the package name. Now, normally that's just an annoying error. You, the human developer, try to pip install it, the command fails with package not found, and you move on. You find the real solution. But threat actors realize something brilliant and evil. They realize that these hallucinations aren't totally random. They're probabilistic. If an AI suggests a fake package name to you, it's probably suggesting that same fake name to thousands of other people who ask a similar question.
Oh, I see where this is going. This is bad.
It's very bad. So the hackers can essentially probe the AI. They can ask it, what packages would you recommend for X, Y, and Z? The AI lists some real packages and some fake hallucinated ones. The hackers then go to PyPI or NPM, and they register those fake names.
They create the package that the AI dreamed up.
Yes, that is genius in a truly evil way. They are squatting on the slop, the garbage output of the AI, slop squatting.
Wow.
So now, when the next developer comes along and asks the AI for help, and the AI suggests a React code shift, which is a specific case study mentioned in the report, the developer copies the install command, runs it in their terminal, and it actually installs.
Because a hacker made it real.
The hacker made the hallucination a reality. And the developer thinks, wow, the AI was right, this package exists and it works. Meanwhile, they just installed malware onto their system.
So let's talk about React code shift. The report says this was a hallucination that took on a life of its own.
It's a fascinating case. React code shift was a package name made up by a large language model sometime around mid-October 2025. It did not exist. But when the researchers went looking, they found that this non-existent package was being referenced in 237 different GitHub repositories.
Wait, 237 people put a package that didn't exist into their project's dependencies? How does that even happen?
That's the key question. It wasn't necessarily 237 people. This brings us to a new concept that the report highlights: agent skill files. This is a really important shift in how software is being built.
Agent skill files. What are those?
Think of them as recipes or instruction manuals for AI agents. If you are building an autonomous AI coder, an agent that can write its own software and manage its own projects, you give it a skill file. It's usually just a text file, like a Markdown or a YAML file, that contains instructions.
Yeah.
Here's how you handle React components. Here's how you handle database migrations. It's a knowledge base for the bot.
I see.
And these skill files are being shared all over the internet. They're copied, pasted, forked on GitHub, translated into different formats. And the researchers found that these skill files, these recipes for AIs, contain the instruction to install React code shift.
So the AI hallucinated the package inside the instruction file, and then humans just copy-pasted that instruction file into their own projects without checking if the package was real.
Yes. Or, even more scarily, other AI agents read those files as part of their training or setup. The researcher, Charlie Erickson, put it brilliantly in the report. He said, skills are the new code.
Skills are the new code. That's a heavy statement. What does he mean by that?
He means that these instruction files, these markdown files, they don't look like dangerous code. They look like friendly, human-readable instructions, text. But they are effectively executable because an AI agent will read them and then execute the commands it finds inside.
So if the instruction says install React code shift, the agent just does it.
It just does it.
Yes.
It doesn't ask, hey, does this package actually exist? Is it trustworthy?
It's blind trust by robots, exploited by hackers.
That's the perfect summary. The AI agent doesn't have the skepticism or the experience of a senior human developer. It doesn't check the download count. It doesn't check the release history. It just follows the recipe. And if the recipe is poisoned because of a hallucination that a hacker anticipated, well, you have an automated, scalable supply chain attack.
That is terrifying because it scales so fast. You don't need to trick a human anymore. You just need to trick the model that writes the instructions that the human or another bot will copy.
Precisely. And it creates a dangerous feedback loop. The AI hallucinates a package. The hacker registers the package. An AI agent installs the package and commits the code to a public GitHub repository. Other AIs then train on that GitHub code. Now, the hallucination is validated because it exists in real-world repositories.
It becomes truth through repetition.
It's a form of information laundering. It's a corruption of the global knowledge base that these AIs are built on. And React code shift is just one example that was caught. As we rely more and more on AI to generate boilerplate code, to suggest dependencies, to write these skill files, this attack vector slop squatting is going to absolutely explode.
So we have the BAS dictionary, RAT, we have the targeted NPM phishers, and now we have AI hallucinations being weaponized. It feels like the walls are closing in a bit. What do we do? How do we defend against this?
Well, let's break it down by audience because the advice is a little different for each. First, for the developers, the humans sitting at the keyboard.
One's typing pip install.
Yes. The days of blindly typing pip install or npm install based on a gut feeling or a quick Google search need to be over. You simply cannot assume safety anymore.
But I can't audit every line of code in every dependency. I mean, Spellchecker probably has its own dependencies, and those have their own dependencies. It's turtles all the way down.
You can't audit every line, no, that's
Yeah.
impossible. But you can check the metadata signals. You can do some basic due diligence that takes 30 seconds. Remember the dormant phase we talked about with Spellcheck
Right, the early versions with no trigger to build trust.
If you see a package on PyPI that has a very short history, maybe it was created last week, or it has a weird versioning cadence like jump from 1.0 to 5.0 overnight, or it has a brand new unknown maintainer,
Oh.
that's a red flag.
So it's about looking at the project's history and behavior.
Exactly. Check the repository. Does the PyPI page link to a real GitHub repo? Does that repo have activity? Does it have issues being reported and closed, pull requests being merged? Or is it a ghost town that was created yesterday with one single commit?
Basic project health signals. Don't just look at the name, look at the life of the project.
Exactly. And use tooling. There are a lot of good security tools now that can be integrated into your development lifecycle. Some of them scan for malicious behaviors, not just known signatures.
What's the difference?
A signature-based scanner looks for things it already knows are bad, like the hash of a known virus. A behavior-based tool watches what the code does. It might have flagged that test file function trying to decode and execute code from a JSON resource file, because that's very unusual and suspicious behavior for a spell checker.
Okay, that makes sense. So what about the AI side? If skills are the new code, how do we secure the skills? That seems much harder.
It is harder because it's a newer problem. If you're using an AI coding assistant, you have to treat its suggestions with extreme skepticism. Think of it as a very smart but very naive junior developer.
It might have a great idea, but it has no security sense.
None. So if it suggests a package you've never heard of, you have to verify it exists before you put it into your requirements.txt or package.json file. Go to PyPI or NPM yourself. Look it up. See if it's a real project with a history.
Don't let the AI do the shopping for you without checking the receipt.
That's a great way to put it.
Yeah.
And if you're one of the people building those skill files or using autonomous agents, you need to build in a verification step. You cannot let an agent execute an install command for a package that hasn't been vetted or explicitly allow listed. We need to build guardrails for the AI agents.
It feels like we need to teach the AI to be paranoid.
We do. Or at least we need to stop infecting the AI with our own bad habit of blind trust. We trust the AI follows instructions blindly, and that's the vulnerability.
At the end of the day, it really does all come down to that one word, trust.
It does. Every single supply chain attack, whether it's a fake spell checker, malicious NPM package, or a hallucinated library, they all exploit the fundamental assumption that if it's in the public repository, it's probably fine.
And clearly, it is not always fine.
The public repository is a wild forest. There are delicious berries and there are poisonous berries that look exactly like the good ones. You have to know the difference, or you have to have a guide who does.
So to recap the journey we took today, we started with a completely mundane pip install. We found a remote access Trojan hiding inside a Basque language dictionary file, compressed and encoded, waiting for a specific secret command to unlock it. We saw how the attacker played the long game with dormant versions to build trust with automated scanners. We tracked the payload to a downloader that called home to a suspicious hosting provider with a history.
The whole playbook.
The whole playbook. We saw the patterns repeating in the NPM ecosystem with targeted fake login screens and crypto stealers. And finally, we looked at what feels like the very near future, slop squatting, where hackers are effectively pre-ordering malware based on the predictable hallucinations of AI models.
It's a comprehensive look at how clever and how patient the bad guys are getting. Hiding inside a dictionary resource file is technically impressive. Squatting on AI hallucinations is strategically impressive. They're attacking the process, not just the code.
It certainly keeps security researchers employed.
That it does.
Before we wrap up, I want to leave our listeners with one final thought to chew on. We spend so much time in the media and in science fiction worrying about AI becoming sentient. We worry about Skynet. We worry about the AI becoming super intelligent and taking over.
The Hollywood threat, the existential risk.
Exactly. But this story shows us a completely different and maybe more immediate threat. We worry about AI being too smart, but right now, the bigger problem seems to be AI being confused.
It's the incompetent but very helpful assistant problem.
Right. It's not trying to harm us. It's accidentally inviting the attackers into our house because it hallucinated a doorman that looked friendly. And if skills are the new code, as Charlie Erickson said, it raises a really weird question. How do we patch a hallucination?
That's a good question.
How do you fix a vulnerability that doesn't exist in any line of code, but exists in the imagination of the probabilistic model that wrote the code?
That is the question of the next decade, isn't it? We know how to patch software. We find the bug, we write the fix, we deploy it. Patching a probabilistic model's tendency to invent reality, that's a whole different and much harder challenge.
Something to think about the next time your AI assistant suggests a quick fix or a new library.
Indeed. Verify everything. Trust, but verify. And maybe don't trust so much to begin with.
That's all for this deep dive. Stay curious, stay skeptical, and please check your packages.
Stay safe out there.